So to jump in, I'm David. I've won probably a dozen plus machine learning competitions on. I had a prior Kaggle account that was top 10, won a bunch on a lot of platforms, built a machine learning driven hedge fund, consult and advise for a lot of startups, and jump in when these competitions seem interesting to me. So really high level, you mentioned this is the only efficiency solution you're interviewing. So I think the main takeaway here overall is that the performance impact of doing an efficient solution was about 8% higher loss. I think in some sense that can be considered low, but I would consider it fairly high. So I think overall I'd probably, looking at these, prefer the main track solutions just simply because the performance was much better. And I think, 10 hours to score 17,000 is pretty efficient in terms of cost and efficiency. So I think there was a competition hosted last year by CommonLit, or sort of one of these organizations where the efficiency prize was almost identical to the main solution track. I think for this particular problem, that's just not the case. So I would generally prefer the full solution over the 8% performance impact. I think second, I had a version of my solution where I simply turned off the neural network and ran just the light GBM. And it actually would have had a higher score and would have been the winning solution ahead of this one. So I think that solution is actually quite useful because it's about 100 times less training, 100 times less disk space, and runs in a number of seconds, much better than the 15 minutes for the full solution. So I think if there was a part of the solution to take forward, it would be just the pure light GBM with no transformer, no neural network at all. So the basics of sort of efficiency solutions, generally what's done is distillation. So models trained, it's a fairly high-powered model. In this case, Jupyter v3 base, sort of a typical, NLP solution, about 12 layers, pretty wide model. And then what's done is the soft probabilities or predictions out of that model are then distilled into a much smaller model. And here, that's the X small model. It's about, I think, 12 layers, but much lower embedding space and much faster. The inference was done on only the student summary without the prompt text. So it had just the prompt title, the prompt question, and the student summary, which was very short, average of about 100 tokens or words. The main contribution of the solution was taking, given the solution is not seeing the original essay text, I did what are known as token type IDs, which were designed originally for basically a question answer situation where you would label the question as a 0 and the answer is a 1, so the transformer knows basically the source of the text. In this case, I used basically 0 to indicate a token that did not occur in the original text that's being summarized, a 1 to indicate that basically that token itself was in the original text, all the way up to basically a 6 to indicate that the original token was there. Both 2 token pairs that included that token were in the original text, all the way up to trigrams. So basically sort of a 3-word phrase that matched the original text. The result of that is the model knows exactly, without seeing the original text, it knows, was this basically a long quote taken from the text? Is it a series of quotes? And basically every word it knows, did it come from the student or did it come from the original text? For the linear models, I basically used a light GBM, which is a gradient boosting model, but I used a feature that's very, very secretly, no one seems to know about it, but it's one of the best features, which is linear trees that fits a linear model inside every leaf of the network. So basically, in this case, I would take the logarithm of all the basically count of characters, words, and so forth, and then it would fit a linear model on that. The best feature was definitely, the number of tokens was actually quite predictive. Just simply, how long was the summary? You generally had about a 0.6 correlation, I think. I had a higher correlation by taking basically a spell check and measuring whether it was a new token that did not occur in the original text. So I think this was basically a measure of, number of novel words that the students wrote that were not in the original text, and that alone gets a pretty high, 0.7 correlation with the ratings assigned. And one of the novel features as well, there was a paper that went around and sort of made a splash a few months ago where they would do, classification of text purely based on when you compress the text, how similar was it to a prompt. So I created something similar to that where I would basically take the Z here, meaning the length of the compression, using just a standard compression library. So I would compress the prompt plus the student summary, subtract out the length of the prompt compressed by itself, and divide by the length of the summary, which basically, if the student copied the text or a portion of the text, it was basically a 0. There's no new information. If their summary was completely novel, you get a 1, meaning it was, completely, pure new information, which, without using a transformer or any neural network or any training, it measures very well, how much new information is there in the summary. So basically, if you combine, the length of it plus a measure of what % of it seems to be new, you get a pretty strong result. Other extras, I'm not sure if anyone else did this, but it seemed like I got much better results by adjusting by each prompt. So subtracted something like 80% of the content score based on the prompt, the mean for that particular prompt, and somewhere around 40% of the wording score as well. The mean was taken out for the prompt, and there might have been some prompts that only had 1 or 2 examples and some with a few thousand. So I used sort of a sliding scale, based on the number of occurrences, I would increase the amount taken out of sort of a normalization. The overall takeaways, I think, are pretty straightforward. In this case, the main solution from the other track, is 8% lower loss than the efficiency track, and I would generally prefer that because while this is much faster, the disk space and the amount of compute required for the main solutions is not that high for the number of essays involved. That said, the pure light GBM solution, if I had submitted it, I only maybe made a few submissions the final day, but if I'd submitted that, it would have been the winning solution. And again, that's sort of a couple megabytes, runs in a number of seconds. So I think that would be the solution that's actually useful, that could run on any almost a calculator actually in terms of compute, and be almost the same performance as this overall solution. That's really all I had. I'm happy to answer lots of questions you have, but pretty straightforward in terms of what it takes for this competition.